Alright guys, today's lesson is on simplifying radical expressions. What you should have in front of you at this point is your notes on simplifying radicals guided notes packet that you're going to use as you follow through this lesson today. So first thing I want to point out to you is that I will probably not be writing every single part of the guided notes packet onto this lesson. So you are required to focus and pay attention so that you don't miss any of the important details. So let's begin by talking about what this little symbol called the radical symbol actually means. That symbol actually means the positive square root of a number. So what this means, if we consider something like the square root of 25, what this really means is that we are trying to figure out what positive number times itself gives us 25. And most of you probably know that one off the top of your head as being 5. So there are certain things called perfect squares, and those perfect squares are numbers that if we took a positive whole number, multiplied it by itself, we would get those numbers. So for example, 4, 16, 9, 25, 36, 49, 64, so on, are all examples of perfect squares. Meaning if we take the square root of any one of those numbers, it's going to give us a nice whole answer of 6 or 5 or 7, whatever that number might be. The problem is the world isn't perfect and square roots aren't either. So a lot of times we end up having something like the square root of 12, or the square root of 27, or the square root of 48, where if we punch that in our calculator, it's not going to give us a nice whole answer. It's going to give us this big, giant, long decimal. So what we're going to learn about in this lesson is how do I take that square root and make it smaller. I just want to simplify it. I don't want to necessarily get rid of the square root symbol. It might happen that way sometimes. But that is not my goal. My goal is not to get rid of the square root symbol. My goal is to make the square root as small as we possibly can. Same thing if I ask you to simplify 3 over 6. You wouldn't necessarily get rid of the fraction. You would just reduce it to 1 over 2. So the same thing, we're just going to try to make our numbers a little bit smaller. So just to start with, numbers 1 through 4 here on your guided notes are all perfect squares, meaning these are ones that you should be able to do right off the top of your head. And if you can't do them off the top of your head, then you could always punch those in on a calculator and see what that would give you. And I'm sorry I said 1 through 4, I meant 1 through 5 there. So the square root of 49, you're asking yourself what number times itself gives you 49? And that would be 7. Square root of 100. So you say what number times itself would give you 100? And that would be equal to 10. I'm going to pause for just about a few seconds here, let you try those other 3 on your own, and then I'll provide you with those answers. Okay, at this point you should pretty much have those. If the square root of 1 is 1, the square root of 144 is 12, and the square root of 0 is 0. So those are all examples of perfect squares. So they worked out very nicely. We didn't have to worry about getting a decimal. We didn't have to worry about doing anything else. The problem is that doesn't always occur for us. So let's take a look at the parts of a square root, and then we'll also talk about how to simplify those. So parts of a square root. The big giant symbol is called a radical. So this is called a radical. And the number underneath the radical, or what I like to refer as the number in the house, inside the house, is what we call the radicand. And again, I refer to it a lot of time as the number in the house. I refer to it as the number in the house. And well, the other arrow that's pointing there is actually in this case pointing to an invisible number. That invisible number for us in this point is a 2 because this is a square root, so there's actually an invisible little 2 right here that we could write in if we felt like it. But that could also be a 3, a 4, or 5. There's things called cubed roots or fourth roots or eighth roots, whatever it might be. That number right there is called the index. It's called the index. So I just wanted to point out the important parts of a radical, so that way you understand what it is that you're looking at. And then when we go to start simplifying them, if I use the word like radicand, you understand what that word means. The next part there on your guided notes says a radical expression is any expression that contains a radical. Pretty easy to remember that one. It's any expression that contains a radical. And I already stated this, but I'm going to point this out one more time in this section right here. The goal of this entire unit is to learn how to simplify radicals. To simplify radicals is to perform every operation possible and to make the radicals as small as possible. Small as possible, that's what we're looking for there. We are, again, just trying to simplify those square roots. One way that we can do that is by realizing that there is this property called the product property of radicals. That product property just simply means that I could take any radical and I could write it as the product of two radicals. So if you see here, for example, the square root of 15, the square root of 15 could also be written as the square root of 5 times the square root of 3. Now, you might be asking, well, what's the need to do that? Well, when we start looking at some other problems, it's nice to know that you could break the square root symbol down into other factors and then work with those factors. So also the square root of 26, that could be written as the square root of 13 times the square root of 2. Not going to really go any further in depth with that property at this point. I just wanted to kind of explain it to you because we will be using that inadvertently when we start simplifying these square roots. So let's get to the nitty-gritty. Let's talk about how to actually simplify a radical or a radicand. So what we're looking to do again is we're looking to make it as small as we possibly can. So I think one of the easiest ways to learn how to do this is to learn it by making a factor tree. And we all should be familiar with making factor trees. That's something that you did pretty commonly in elementary school and middle school. So this first thing here just says, let's make a factor tree for 50. Well, we could start with 25 times 2. We could also start with 5 times 10. It doesn't matter which factors we start with. I'll tell you that typically the smaller factors you can find, the less of a factor tree you have to make. So if I go to 10 times 5, that means I'm going to break the 10 down to a 2 times 5. Now, let's talk about how this is going to help us with a square root. So if I took this exact same problem, but this time I said, okay guys, it's the square root of 50. We're going to do the exact same thing. We're going to make a factor tree for 50, just like we did, either using 10 and 5 or 25 and 2, whichever you prefer. And then this part right underneath here tells us exactly what we're looking for. So I like to refer to this as twins. So we are looking for twins. Twins means two of the exact same thing. Now, if it was a cubed root, we would be looking for triplets. Or if it was a fourth root, we would be looking for quadruplets. But since it's a regular old square root, and remember there's an invisible 2 right here to remind us of how many we need, we are simply looking for twins. So I take this problem, I find the twins. Those twins are 5 and 5. Once I find the twins, I circle them, and they immediately go to the outside of the radical sign. So my 5 goes to the outside. Now some of you might be wondering, why is it just a 5? There were 2 5s, why did it become 1? Because those two twins, those twin 5s, made one group of 5s. That's why there's only one 5 on the outside. And then we look at this problem, we say, okay, well, what's left over? Well, the only thing left over is a 2. And I like to put boxes around things that are left over, which tells me I need to put them back inside the house. So that 2 goes back inside the house. Some of you might be wondering, well, what happened to the 10? Why isn't the 10 left over? Well, what you have to remember is you broke that 10 down into a 2 and a 5, which were then used again. So therefore, that 10 is no longer important to us because we broke it down and used its factors. So, and a couple other important things to note here for this important stuff. It says, as soon as the number kills its twin, it goes outside the house. We could also just say, as soon as the number finds its twin, it goes outside the house. If a number has no twins, it must stay inside the house, which is exactly what we did there with the 2. All the numbers inside and outside the house are multiplied together in the end. So in other words, if you have more than one set of twins and you take those to the outside, they get multiplied together. If you have more than one number left over to go back inside the house or underneath the square root, then they also get multiplied to go back in. And I'll demonstrate that here in just a second. Let's move down to the next part. So let's apply this exact same theory to the square root of 32. So if we're looking at the square root of 32, let's begin by making some type of factor tree. So again, there's a couple different things you could start with. I'm going to go 8 and 4. And that 8 is going to get broken down into a 4 times 2. And the 4 gets broken down to a 2 times 2. The other 4 also gets broken down to a 2 times 2. So I've got lots of 2's in this problem. So again, once I get here to the prime factorization, I look for any twins that I can find. So I've got a set of 2's here, that's a twin. I've got another set of 2's here, which is a twin. So both of those twins have to go to the outside. Now I'm going to write my final answer over this way just because I'm out of room here. So both of those 2's have to go to the outside. And what's left over is only this other 2 that I just put a box around there, which goes back inside. So the 2 and the 2 that were both sets of twins, they get multiplied together to make my final answer of 4 square root of 2. Now, if you're quick enough that you don't need to write out 2 times 2 on the outside of your radical, that's perfectly fine with me. What I do is I just say, okay, here's a group of 2, that's 2. Here's another group of 2, so 2 times 2 makes 4, and I automatically write it outside the radical sign. All right, hopefully you're picking up on this. I know I'm moving kind of quickly. Hopefully you're getting the gist of it, and you're going to be able to practice here in a few minutes. So if I start looking at these practice problems right underneath here, numbers 8 through 10, I'm going to do each of those by making a factor tree. So I'm going to start with the square root of 18, which we can break down into 9 times 2, and then 9 breaks down into 3 times 3. There's a set of twins, goes to the outside. Here's my leftover, stays on the inside. So it's 3 square root of 2. So this lesson, guys, basically generally consists of, can you make a factor tree, can you find the twins? If you can do those things, then you're in good shape. So we are ready to move forward. So if I look at the square root of 60, I can take 10 times 6. The 10 breaks down into 2 times 5. The 6 breaks down into 2 times 3. So I see here that I have a set of twins. They're both 2's. So that set of 2 goes to the outside. And left over I have both a 5 and a 3, which have to get multiplied back together to make a 15 on the inside. I'm going to give you a second here just to try to figure out the square root of 54. And then I'll be back to provide you with the correct answer. Okay, 9 times 6 gives us 54. 3 times 3 is 9. 3 times 2 is 6. Remember, if we're looking for twins, we can only use 2 of those. So I have to only take 2 of these 3's. It doesn't matter which ones I take. So there's your 3. Goes to the outside. And I have a 3 and a 2 both left over to go back inside. So I multiply those together. And I get 6 for the inside of the square root. One last thing to talk about. And the last thing we're going to talk about is what do we do when there are variables included. So if I look at the next part, it says, when there are variables in the radicand, it is assumed that they represent positive values. in this situation, ask, here's what you're ready to write, how many times does 2 go into the exponent? How many times does 2 go into the exponent? How many times does 2 go into the exponent? However many times 2 goes in evenly, goes on the outside. And the remainder goes back inside. Goes back inside. So here it's just basically simple division. Now if we're talking about square roots, again we're using the invisible 2 that can be found as our index above our radical. So you have to remember that that 2 is there because you're going to be using it when there are variables included. So here's your example. The square root of x to the 15th power, I want to simplify that. So I simply ask myself, how many times does 2 go into 15? 2 goes into 15 7 times evenly. 2 times 7 is 14. With a remainder of 1. What that means is that on the outside of the radical, I'm going to have x to the 7th power. See, that's 7. That evenly became my exponent. And left underneath that square root symbol is the one remaining x that did not go in evenly. Sounds a little confusing, but it's not, I promise you. So number 11 here. 2 goes into x squared just one time, and it goes in completely evenly, which means the square root symbol is completely gone, and this would simply be x. The square root of x squared is just an x, because 2 goes into 2 one time, no remainder. Looking at number 12. 2 goes into 3 one time, so there's one y on the outside, with a remainder of 1, so there's one y on the inside. 2 goes into 4 with that exponent twice, so it'd be z squared, there's your 2. 2 goes into 4 2 times, with a remainder of nothing. No z's are left over, so there's your final answer. And you do the exact same thing for number 13. So 2 goes, first of all, when there's a number included here, we'd have to make a factor tree for this, which just gives us 3 times 1, doesn't simplify any further. So that tells me that the 3 is going to have to stay inside the house. And then we ask ourselves, 2 goes into 22 11 times with no remainder, so it's 8 to the 11th times the square root of 3. All right, at this point, you are ready to turn to the next page, which is your homework section. There are 19 problems on there for you to do as homework. I'm going to go through and just do a few of those with you, just so I can make sure that you understand a couple of these. So I will do numbers, let's say 6 and 15. Let's do 6 and 15 together. So for number 6, again, you're going to make a factor tree. So I'm going to go 6 times 8. 6 goes to 3 times 2. 8 goes to 4 times 2. And 4 goes to 2 times 2. Looking for my twins, I've got a set here, and I've got a set there. So that's a 2, one set of 2 times another set of 2, which makes 4. And my leftover is a 3, so it stays inside. It cannot come out to play. Looking at number 15. All right, I wanted to point out 15 because if you notice, there is already a 2 on the outside of the square root symbol. Now, if you know your perfect squares, and you know that the square root of 4 is 2, you don't need to make a factor tree. But if you don't, you make the factor tree for 4, you're going to get a set of 2's. There's your twins. when they go to the outside, since there is already a 2 out there, they have to get multiplied by that 2 that's already outside. So this group of 2 times this 2 that's already there makes the outside a 4. Then you say this invisible 2 goes into 2 once with no remainder, so x is going to stay on the outside. 2 goes into 7 3 times with a remainder of 1, so you're going to have 1y left on the inside, 3 on the outside. And 2 goes into 9 4 times with a remainder of 1, so there'd be 1z left over on the inside. So final answer there would be 4x y cubed z to the 4th times the square root of yz. All right, good luck with the rest of your questions here on numbers 1 through 19. We will be looking at these problems at the beginning of class on Monday. So if you're completely stressed out about it, talk to a neighbor, see if somebody can help you a little bit. I promise you, this is a really easy section. Again, it consists of, can you make a factor tree? Can you find twins? And can you take 2 and divide it into exponents and figure out how many times it goes in evenly and how many remainders there are? Other than that, there's not a whole lot to it. So we will discuss this on Monday. Have a great weekend.